Okay, let's get started. So welcome to the AFMS seminar this week. And it's my pleasure to introduce Dr. Jisheng Zhao from Monash University. He got his PhD in 2012 at the Monash University. And after having some research experience, he recently got the RARC Dekra position. His main interest is fluid structure interaction and structural vibration control, which is obviously important in industry. And the title of his talk today is Active Control of Flow-Induced Vibration of a Circular Cylinder. Okay, over to you, Jisheng.
Thank you, Kengo. I would like to thank Kat and also Turan. They invited me to present this talk, and also thank you for coming. So today's talk, the topic is active control of flow-induced vibration of a circular cylinder. So I'll start the talk with, okay, firstly, a little bit about myself. My research interests include fluid structure interaction, flow-induced vibration, and also recently I've been looking at the flow energy harvesting. Broadly, I'm interested in aerodynamics of the insect flies, vehicles, wind turbines, etc. And also I look at weight transitions, and also I try to apply real-time control system to control the structural vibration as well. I'll leave that presentation today. I will give you a brief introduction of the research topic, flow-induced vibration. And then I will show you two typical body oscillator phenomena of FIV. So the first one is due to the vortex setting instability, what we call vortex-induced vibration. And the second one is galloping. Galloping is a term used more commonly by civil engineering community. And galloping is due to movement-induced aerodynamic instability. I'll give you some more details later. So to show you these two body oscillator phenomena, I'll give you an example of FIV of a square cylinder to demonstrate you what's the difference between VIV and galloping. And the second part of the talk, I will show you some experimental results of active control of FIV of a circular cylinder. Basically, we impose body rotation to the cylinder, and then we look at the control effect, say enhancement or attenuation of the vibration. So there are two cases I will show you. The first one, we will look at the cross flow directions of the body vibration. And the second part, we will look at the inline structural vibration. So inline, which means the vibration direction is in line with the flow direction. And lastly, I'll give some conclusions of the talk. All right, some background or motivations for our research. I'm sure you have seen this before. If not, I think this is quite a famous example of flow-induced vibration. We're looking at the Tacoma Narrows Bridge, which crashed in 1941, just a few months after it was completed. So in this example, actually, if we pay a little bit attention to the background, you can see the wind on the day. The wind speed wasn't that high. You can see from the trees, right? But actually, the vortex jetting past the bridge caused initialize the structural vibration, and then because of the bridge, the cross section is not a circular cylinder, it's a rectangular cylinder, and then it will experience what we call galloping. But here we have a problem of two-dimensional, two degree of freedom problem. So we have the pitching and also heaving vibration as well. Anyway, I will show you another example where FIV is important as well. So we're looking at the tails of this aircraft. You can see the tail, the horizontal tail, can experience some wobbling, and also you can see it has two dot vibrations as well. So this is very risky to the structural stability. And more broadly, you can see applications of FIV in different fields of engineering. Say civil engineering, we have high-rise buildings, bridges, things like that. This is in Brisbane, so you can see this is like a circular cylinder, and this is like a rectangular cylinder. And more commonly, you can see in the offshore engineering structures, like oil risers, basically the circular pipes, pumping, sucking the oil, the raw product from the sea bottom to the platform, the oil rigs. And of course, there is current, so there will be water shedding to cause the structural vibration as well. And more recently, people are building offshore wind turbine farm. So here we can have different problems of flow-induced vibration. For example, you have current, and also you can have airflow as well. And FIV problem also can be seen in the air engines as well, like the blades, basically the airflow structures, and then they can experience structural vibration as well. So that's why FIV is important. On the other hand, we're trying to extract energy through the structural mechanical vibration of FIV. We can convert the mechanical vibration into electrical energy as well. So this company, they propose what they call bladeless wind turbine. So basically, there's a damper, and then the cylinder will oscillate. We can convert the oscillation into electrical energy. There's another example. There's a numerical study that I did with my colleagues from China. So we were looking at flattening foil numerically, trying to understand the energy harvesting performance from flattening foil. All right, so some fundamentals of FIV, if you are not familiar with this. So FIV, we can categorize them in terms of the source of excitation. So as I just mentioned before, we have the water-induced instability. So this is the first one, that's a more typical one, so which is a VIV. Usually when we start a VIV, we use the classic model, which is a circular cylinder, because it's easy to define the body. You just need to have the diameter and also the length to define the model. And in the middle, we have some external induced excitation, like perturbations and things like that. We are not interested in here. So on the other hand, we have the movement-induced excitation. Basically, when you have a body moving in a flow, relatively to a flow, you have a speed, say a vertical speed, which is will have an angle with the oncoming free stream velocity. Basically, there will be a relative velocity. So the pressure or the forces, if you integrate all around the surface, it might be in an angle in favor of the body oscillation. So which will enhance the structural vibration. In that case, the body will experience low frequency oscillation, but with large or even unbounded amplitude of structural vibration. So a typical example is a square cylinder. I'm going to show you. So to model this mathematically, it's quite simple. probably not simple, but here we just want to make our life easier. We just use a linear model, a linear mass damper spring system to represent our problem. So here, the governing equation, basically you have a linear second order equation. You have the mass, and then the y dot dot is the acceleration, and c is the damping factor, and y dot, which is the body speed. K is the spring constant, as you can see in the schematics here. And the Fy is the cross flow or transverse force acting on the body. So in our studies, or in my studies, I typically look at one dot system, say the cross flow system, or inline vibration case. So anyway, we can use some dimensionless parameters to describe this equation as well. Say we will use the damping ratio here, and also the mass ratio. The other term is important as well. Anyway, I will introduce them later. So this is the water channel facility that I've been using to run the experiments. So basically, the water channel has a working section with 0.6 meter and 0.6 meter in width, and 0.8 meters in depth, and 4 meters in length. So the velocity range, we can run it from 50 millimeters per second to 450, sort of this range. And depending on the structure size, the Reynolds number range that we can look at is 50 to say 20,000, or even slightly higher. So to simulate the mass spring damper system, I built an air-bearing system. This is the drawing from 3 different views. So the top view shown here, this is the air-bearing structure placed on top of the water channel. So the flow is coming from the left to right. So we have a pair of springs, extension springs, to constrain this slider actually here. I'll show you some photos later. So this is the slider, can slide on the 2 precision shafts, the guide shafts. So the spring just provide the constraint to let the slider to oscillate back and forth. So this is the side view. For example, we mount a cylinder vertically. So this is the free surface of the water channel. So we have a platform as the end condition platform, just to promote parallel shedding. So this is the back view of this air-bearing setup. All right, some parameters that are important to the system. So for example, here we have the natural frequency of the system in still water. And then we have the structural damping in air. We consider this is can be approximated to the structural damping in vacuum. And the other structural damping ratio we would use reported in our paper is, okay, we consider the AFMS effect. So on the other hand, the mass ratio, which is defined as the total oscillating mass to the mass of the displaced fluid. So this is important as well, because if we run the experiment in wind tunnel, the dynamics could be very, very different. And we normalize the flow velocity based on the natural frequency in water and the geometry size, so the diameter of the circuit cylinder. And sometimes Reynolds number is also important. It could be quite sensitive in some experiments. But anyway, in my study, the Reynolds number will vary from 1,500 to 20,000, something like that. So to give you an example of a VIV of a circuit cylinder, I'm showing here the amplitude response and also the frequency response as a function of the reduced flow velocity. As you can see here, on the top here, we have three different branches defined by Clark Williamson, because they first look at this low mass ratio problem. For the initial branch, you can see correspondingly here, you can see two frequency components, with one matching the natural frequency of the system in still water. The F star is normalized by the natural frequency of the system already. So one means the natural frequency in still water. So the other component just following a slope. Actually, the slope is the through-hole number of frequency, the normalized through-hole number frequency, which is about 0.2. And as you increase the reduced velocity, so you can see these two frequencies, they're going to meet, they're getting close together. And then the structural vibration amplitude will experience a sudden jump from the initial branch to the upper branch. So where what we call the lock-in or synchronization start. And as the U star is further increased, it would jump from the upper branch to the lower branch, where the frequency become more stable because of the mass effect of the system. So it's not locked onto F star 1. Okay, it's just a shift, kind of the shift is related to the mass ratio. There are some studies discussing this problem. And before the increased V star, the system kind of maintain the lock-in or lock-on or synchronization anymore. So the system will experience this synchronization. And then you can see the two frequency components again, with one matching the water shedding frequency of say a fixed body, but the other a weaker component matching the lock-on frequency. All right, so this is a typical phenomenon for a circuit cylinder. So to show you a little bit more about the square cylinder case, during my PhD study, I was looking at the FIV of a square cylinder with mass ratio, but I vary the angle of attack, okay, because it's reasonable, right? In our engineering, in wind flow or in any even in current, if it is a structure, the flow might come in any direction. So here I vary the angle of attack, say alpha. So as you can see here, at zero degree angle of attack, so we can see a typical response of galloping. So you can see that the amplitude increased in a kind of a linear change with a U star. If you pay a little bit attention to the amplitude magnitude, you can see it's more than 1. But if we come back here, you see for circuit cylinder is a VIV. VIV is a cell limited. So typically the amplitude is of an order of a 1 diameter. But for galloping, it can go even higher amplitude, larger amplitude, much larger amplitudes with increasing U star. But due to the limit capacity of the rig, we couldn't go further. And then the other case that we consider is like a 45-degree case, which like a diamond. The diamond case will, well, in terms of the geometry, it will look like a circuit cylinder, but it will have a fixed separation point at the top corners. So in this case, for the diamond, it experiences a VRV dominated feature. So we label it as a VRV response. Okay, so there's a question for us to answer. So what if you change the angle of attack, right? This should be a transition from galloping to VRV then. And I did a series experiment. Just change the angle of attack by 0.25 degrees. And then interestingly, we find a new branch, what we call higher branch. Actually, it's not a VRV upper branch. So this is the normal VRV branch, but there's a new branch called higher branch, which is associated with subharmonic frequency, which occurs over the range here, 10 degrees to 22.5 degrees. This is the normal upper branch when it occurs. All right, and then I look at more carefully how the frequencies vary with the U star for different regimes. So for example, actually for the 0 degree case, it's not pure galloping either. And then there's a kind of a combined effect of a galloping and VRV, say, in this region. You can see this is a third harmonic frequency component. But this one is the dominant frequency component. It's not locked onto the natural frequency either. And I find that there's off synchronization phenomena in the square cylinder case. But for diamond, if you look at that, as you can see, is more like a circular cylinder in terms of the frequency response style. And for the higher branch, so we just want to show you that there's a subharmonic frequency component in the higher branch here. So which is quite interesting. And then I use PRV to look at the water sharing mode, which is quite interesting. There was a 2-2S mode, which means that there were two. For circular cylinder, you have the initial branch. You have two single vortices shared per cycle, and in this case, because of well, associated with subharmonic frequencies, and then it sheds two times 2S mode. Anyway, so from the square cylinder, we understand that when we change the angle of attack, the after body will change. So basically, it will break the axial symmetry of the system. That's why the transition from galloping and VRV happen. So, which gives us a thinking that, okay, for circular cylinder, how can we break this axial symmetry? So we are going to apply notation to the body to break this symmetry. Before I talk about that, I will show you what we call the Magnus Effect. There's a video. I'm not sure you have watched it before, but I think it's quite interesting. Basically, these people drop a basketball from a high platform and straight. You can see it when it was dropped straight, it just falls straight down. But when you spin the ball, the ball can fly, right? This is due to the well-known Magnus Effect. I think back to 1920s and 1930s, research on Magnus Effect and try to apply the effect. That was quite intense. I think there was lots of experiments going on a century ago. So basically, when the surface of the ball or cylinder has a velocity to the floor, and then it can generate a side force. Okay, so there's some background about the Magnus Effect. So it is named after Magnus, who observed this phenomena in 1852. in the little that was in a simple wind tunnel experiment. Not wind tunnel, it's a blow fan, and then there's a spinning cylinder, and then you saw that the cylinder tend to go to one side. Anyway, so this is a schematic I use in the active control cylinder. So I call it active control because we input energy to the system. So we have the parameter of rotation rate, which is normalized by the free stream velocity. Basically, it's the surface velocity divided by the free stream velocity. So this is the setup. On top here, the two figures are schematic drawings, and then here's the photo. Oh, I think I have a. Can I zoom in a bit? Anyway, whoops, sorry. I want to go back. This the air rig that I use. You can see this the slider. This is this block. So it sits on the two shafts. We supply condensed air. So inside the slider, what we have is air bearing, which has porous surface. Basically, the compressed air escapes through the porous surface will form a thin air film that can work as lubricant. So, which is pretty thin, like 20 to 30 micron. All right. And then here we have a stepper motor to provide the rotation motion. That is the model cylinder that we spin. All right, so to show you the results, first we're looking at a non-rotating case. You can see here we have the typical 3 branches response, the initial branch and upper branch and lower branch, and followed by this synchronization region. And we gradually increase the alpha, which is the rotation rate, to 0.5. You don't see much impact yet. But gradually after 1, you can see some enhancement to the peak amplitude. Up to 0.5, 1.5, you can see pretty much like 60% increment over the non-rotating case. After 2, this is about 80% increment in the peak amplitude. And you can see also the high, there's some marginal impact on the lower branch. But further increase in the alpha, to 2.5, you can see the sudden drop, right? So which means the rotation is not going to enhance the FRV amplitude anymore. It's going to attenuate it. But interestingly, you can see two peaks here. For the increase to 3, alpha 3, you can see quite close to suppression. Up to 3.5, you can see suppression with the suppression. Right, and then we try to look at more carefully, and then we select a few different U stars to represent different branches, and then we look at a fine increment of alpha. So shown here is from the initial branch. Basically, we find that for alpha larger than greater than 2.3, you can see full suppression. This is for the initial branch. But in general, it doesn't have much impact on the amplitude of the initial branch before the drop. The frequencies here showing that, okay, we have this the natural frequency of the system, as you can see from the non-rotating case as well, and then this the Schumann number frequency as well. So they will become desynchronized for the suppression region. All right, this is the for the upper branch, which is U star 6.25. You can see a quite obvious enhancement in the amplitude, but suddenly it drops at alpha about 2.3 as well. So we look at the wave structure before the drop and in the drop after the drop. So basically, we have a very well-defined 2S mode on here on one side, and the other we call coalescence of asymmetric vortices like this. Basically, there's no well-defined water shedding. Just like the larger scale structure vortices break down there. And we look at the beginning of the lower branch, and there were two different modes, water shedding as well. And before there's a sudden drop, which is a 2.3, and after the drop. So, which means that the wave mode associated with the rotating cylinder is a rich of variety, and also you can see even the U stars are slightly increased. The response, this one, the beginning of the low branch and the middle of the low branch, they're quite different as well. So which means the dynamics there is quite sensitive to the U star as well. And we look at the synchronization region, but we didn't expect this increase. So anyway, we try to understand why. I think when the frequency just try to I think it just become more clear with the one frequency component there. So it becomes more regular. I think that there was a little bit become more regular. I mean, the water shedding. So there was some increase enhancement there. All right, and then we did a lot of experiments that was done by my previous PhD student, and we look at the different wave modes. We just do some spot measurement using PRV on the map. If we plot the amplitude contours as a function of alpha and U star, this is the amplitude contour plot, and then we try to define the water shedding mode in different regimes. So we find that a variety of wave modes are quite complicated, and sometimes you can find the wave modes, they are not stable, they can switch in time as well. So quite complicated. And just try to show you the wave mode switching behavior. For example, here we can observe a P plus S mode, a P here, which means a pair. So it's termed by Williamson and Roscoe when they observe the wave patterns behind a force oscillating cylinder. They term, okay, a pair shape per half cycle, they call it pair. So anyway, here we have a pair plus a single, S represents single vortices shape per cycle. So to show you that the points, okay, this is a time trace of the cylinder oscillation. So the change, there's some change, like for example, there's a pair plus S. S is okay, the S plus, which means the positive vortex, which is in the anti-clockwise direction, which is in red, okay, represented by red color. So you see the wave mode switching from a P plus S to a 2S mode here. I think there's a video to show you this. So the top point is the cylinder position. It will start to oscillate. And these plots are the POD modes. We plot the phases between the two different POD modes. So when it enter the blue zone here, we have a P plus S mode. So the switching behavior causes some problems to us because we have to manually to look through all the data. If we do a phase average based on the oscillation phases, we could just easily miss the weight mode switching behavior. Right. Sorry about that. My keyboard somehow. Look at this already. All right. Okay. Ooh. It's hard to navigate. I want to go back to the damping effect slide. Okay, sorry about that. Okay, more recently, I'm looking at the effect of the structural damping. Actually, it is combined effect of structural damping and the alpha, the rotation rate. So I just did the experiment very recently. Just finished last week. Okay, we're looking at the. I pick up the alpha value at 2 because you could see that at alpha 2, you can see the largest enhancement in the amplitude. Right? So that's why I picked up alpha 2, and then I changed the structural damping. I have a damper, the G, which represents the gap of the damper elements. Anyway, you don't need to worry about that. So we have a structural damping. We can change it over 20 times, right? More than, okay, just about 20 times. So you can see here, as the damping ratio is increased, you can see the upper branch gradually disappear up to, say, this damping ratio. The gap is like 9 millimeters. And also, I did the experiment more carefully now. You can see the lower branch, there's a V-shaped drop. I didn't expect this, but anyway, I try to explain it a bit more later. And the symbols in the gray color represent the case of the non-rotating cylinder. So you can see that for the non-rotating case, even I increase the structural damping to the same level as the rotating case, but the non-rotating case, you can still see significant structural vibration. But for the rotating case, you can see it's pretty much suppressed already. So which means that the rotating case is quite sensitive to the change in structural damping ratio. And then the other 2 plots. So I try to understand the Magnus force, how the structural damping can influence the structural vibration or the Magnus force. So basically, I could use this equation I derived from the governing equation of motion. What I find is that the structural damping has a minimum impact on the Magnus force. Basically, it could follow this line nicely, except for the region that we have this structural, where the structural vibration is large. Okay, so anyway, so which means is the vibration is quite sensitive to the structural damping for the rotating case. And then if we look at the frequency control plot, you can see that different from this is in non-rotating case, right? We have a third harmonic here for the non-rotating case, but actually for the rotating case, we found that, okay, this is a second harmonic instead. That's why, and this second harmonic is quite sensitive to the change of the damping. And then we look at the flow patterns, the way from the initial branch, this is the initial branch, and the upper branch and lower branch, and then this how the damping ratio is changed, right? Because the damping ratio is increased in this section in the column, compared with the non-rotating case. So for the initial branch, it's like 2s mole, but for the rotating case, it's like, okay, it's deflected by the rotation. But for the upper branch, it's very different. So we have a pair plus s mole here, what I call. So it's quite, it can exist up to a certain, up to this point, up to this damping ratio value. But later, when the upper branch disappear, we return to a 2s mole. For the lower branch, where we observe a V-shaped drop, we can see that it's initially for lightly damped case, it was a pair plus pair, a V pair. But in the V-shaped region, actually the vortices just break down easily. So that's why it cannot maintain very large amplitude. So that was why it was so sensitive to the change in structural damping ratio. All right, the other case I'm trying to show is the inline oscillator vibration case. We have a similar equation for the motion. You just replace the y with x here. So this Rick setup photo. Anyway, and, skip this. All right, right here. So we're looking at the amplitude response as a function U star. Okay, so typically for a non-rotating case, the inline vibration has a very small amplitude, like 0.1 diameter, as you can see the circle symbols. Okay, and to show you this, the alpha range are divided into different plots. So the upper plot is to show you where the amplitude was small, and the other, the lower one is to show you when we have very large amplitude. So what we find that for the inline vibration case, very large amplitude can occur over the range, alpha range of 2.2 to 3.15. Is what I observed in the experiment, which is quite different from the numerical estimation. Anyway, so this is the 3D plots for different views. Okay. And then I also performed some frequency analysis. So here is the structural vibration. So you can see here it locks on. It's a body weight synchronization, and correspondingly, this the driving force frequency. You can see very clear harmonics. The second and the third harmonic associated with the large structural amplitudes. I think I need to speed up a little bit. Anyway, and then I look at more carefully for fixed U star again, but I increase I change the alpha in a finer step. So you can see this the range corresponding to large amplitudes. This is about 2.2 to 3.15, and then I similar to the cross flow case, and then I spot some VIV measurements here. So I find that there were some weight, different weight modes associated with different regimes. So what I observed that in this regime, the vibration is more like a galloping response. I'm going to show you the waymo. Oh, sorry, it doesn't work. CI mode. I have to click the videos here. Okay, this is the first region we call CI mode. And so this is a bit more interesting. This is a 2S mode. So for a fixed body at this alpha, say at this alpha value, we expect the regular water shedding to be killed by the body rotation already. But interestingly, for the inline case, if you keep the degree of freedom inline, you can see the water shedding again. That was quite interesting. Oh, they don't work. So but this one, even you can see very large amateur vibration, and you can see the elongated shear layer. I mean, it was shed. Some big vortex structure in the wake. Okay, I think this is my talk. So we look at the vibration, FIV of a square cylinder. Oh, I mentioned B section. Sorry, I didn't present the B section. So there was a transition from galloping to VIV, okay, in terms of the angle of attack, which means the upper body is important, and also when we change the axial symmetry is important. And then we try to control it based on the body, the system's symmetry, which is for which we use the body rotation to control. And a rich variety of waymo observed, and also some switching behavior. We still don't have a full understanding why this will happen. So I try to use some chaotic analysis to look at that. And for the inline case, which is interesting, we didn't expect the very large amplitude. Imagine that for a non-rotating case, we have a 0.1 diameter oscillation amplitude. But if you impose a rotation, you can enhance that by 10 or 16 times. You can go up to 1.6 diameter. Some related publication, maybe some future work. I'm looking at feedback control because in these experiments I just use a stepper motor, which doesn't have a feedback device to control. I'm upgrading the motor system to be a servo motor, and then I want to control the system maybe based on the phase. I want to play around the force phase and also structural phase, the structural vibration. Right? Okay, I think this is my talk. I think I just go over time a little bit. If you have any questions, please.
Yes, thank you, Jisheng, for a very stimulating talk. So if you have any question, just unmute yourself. Or you can raise your hand in Zoom. It's a really interesting talk. I have some comments. Am I correct to say that earlier you mentioned about it has some relevance to energy generation, electric generator. Am I correct to say that the larger A, the more we have electricity?
Not really. It depends on the, imagine that if you have an energy generator, you have to overcome the resistance to drive the mechanical components, right? And that's why we use the damping effect to try to simulate that. And also, actually, if you look at the power equation, the power is defined as the dot product of the force and also the velocity. So it is you need to have the force in line with the velocity to generate more power. So which means it's not necessarily corresponding to largest amplitude vibration.
I see. Okay, so it's linked. So Richard,
yeah,
I
it's
guess
kind of a balance you need to integrate.
Yeah, it's complicated phenomena. Richard, I guess you have a question.
Hi, Jisheng. Great to see you.
Hi.
Congratulations on finishing your latest set of experiments, and thank you for sharing. My question is, have you got any feeling for how much power you can get out for the power that you put in? Yeah.
Wow. Good question. Well, I think for a non-logical case, you can get a power coefficient like 0.18 from our experiments. I think that depends on the, I don't know, to be honest, I don't have an exact answer for that. Well, I think we need to explore it further.
Okay, no problem.
Collecting foil could be a better option, maybe.
Oh, absolutely.
More questions?
Yep.
Yeah, so
oh, sorry. You go if you want. Yeah. I had a quick question.
Go ahead.
Hi, Kat.
Oh, hi. Thanks for the talk. That was really cool. I did have just a question. You mentioned near the start about the Reynolds number and that it was sensitive in some experiments. So first of all, so your Reynolds number in your lab experiments, what I think is like 1,000 to 20,000 or something. How would that match up with like one of the applications, say? So like maybe the renewable energy extraction application. Is that kind of similar Reynolds?
It could be slightly higher in real application because in here we have a circle like in diameter is like 30 millimeter, but I think you can scale up a little bit more. And why I said it was sensitive to Reynolds number because there was a publication, not from our group. They published a paper in POF, and then it showed that the amplitude, they didn't even observe the enhancement at low Reynolds number. That was from 500 to 900, I believe, the Reynolds number range. So that's why I think it's quite sensitive to Reynolds number.
Would you think about running a bunch of different Reynolds numbers, or at least, I guess, looking at a little bit more at the Reynolds number?
I think it's
other stuff you want to focus on.
I think it's limited by our water channel facilities here. Well, if we could have a wider water channel, I think. Anyway, there's some studies showing that with increase in Reynolds number, you can see some improvement in the energy output as well.
Okay. For
the non-rotating cylinder.
So it's kind of an unfair question to ask someone doing lab experiments, sorry. But you answered it well. Thanks.
Thanks.
Okay, thanks, Kat. Any other questions? Yeah, so am I correct to say that when you have ordered flow state, we have a larger amplitude in general?
Sorry?
When we have organized or coherent vortices, maybe we have...
you mean synchronization?
Yeah, I'm interested in flow regime. So you showed some pictures, but in general, maybe we can say that when we have some ordered, Kalman vortex-like state, probably we have larger amplitude. And maybe you have some idea to apply some control to have that state or to avoid such state.
Yeah, that's why we introduced the body of perturbation we try to affect the surface speed, and then thus we can change the water shedding mode somehow. And I think we would just look at the feedback control of the sphere already. We find it quite interesting. We can change the we can adjust the phase between the Fully force, say the phase between the Magnus force and the structural vibration position, say the cylinder position, and then we could control that quite successfully. Sorry, I didn't present the results from that paper. It's published in JFM.
Oh, I see.
Last year, yeah.
Okay, so somehow you can logically come up with controls.
Yeah, we could use the use the body location to modify the flow structure. And we change it to very high frequency, particularly I think it's like 30 times of the normal water shedding frequency. You can really affect the structural vibration.
Yeah, that's really interesting. Any other questions? If not, let's thank for speaker again. Thank you, Jisheng.
Yeah, thank you.